All right, hello everyone. So these tutorials, so we'll have tutorials today and also on Thursday. And the hope is that for those of you that are just starting out doing machine learning and looking at these topics, this might be helpful to get you started. And most of them should be fairly simple. They're all on Colab. And hopefully they should be fairly quick to run. So that we're not going to have you train very large models here because that would take forever. And so the links are here. I sent the links in the Slack, but also you can also just go to just.github.com/PeterParody, and that's just my GitHub. And it should be this first one here with the links. So I'll give you a second to open that up. And so the way we have this set up is that, at least for these first two, is that we'll have the tutorial in a note in one of these Colab notebooks and a couple places in the notebook left blank for you to fill in, but also the answer key in case you just want to take a look and see how all those pieces work. And I'll try to walk you through the broad strokes of the code and maybe get you a sense. So the first tutorial we're working on is this emulators tutorial. So I think a lot of this material is related to what you saw this morning, and also maybe a little bit of what you saw yesterday as well. And the idea is to emulate dynamical systems. And so I guess just to start out, I would have all of you. I don't know how many of you have used Colab before. Just raise your hand. Okay, so I think most of you. So yeah, we have it set up as a Colab notebook, so you can go ahead and open the one labeled tutorial, and hopefully this is what you'll see. And then if you want to be able to edit it, I would just click copy to drive, and so it'll make a copy for yourself, and then that way you're not sharing the same copy of the code. So yeah, let me know if anyone is having trouble with that. So just to give oh yeah. Sorry, what? It's the URL. Oh yeah, I think the link is in the Slack if you have that, but you can also just go to just.github.com/PeterParody, and then all the links are here as well. Maybe I can it's a little bigger. That doesn't really see it. How? Yeah, the links are also in the Slack if you have that open. Okay, so I guess we're a little short on time, so let me get started with this tutorial. So this is going to be a tutorial on training neural network emulators for dynamical systems. And the goal here is, the simple goal is to take a data set or either from experiments or observations or simulations and train a neural network to emulate that dynamical system and act as a model for that system. And there are a couple reasons why you might want to do this. First is very simply just to accelerate a simulation or model of some unknown dynamical system. And often it's used often the learned models are a lot faster than the existing physical models, or if you just don't have a model for it, it provides you with a model. And some common examples are there are these large-scale weather or climate simulations, and those are very expensive to run. So you might think maybe I should build an emulator for that and be able to run those simulations faster. Another example that maybe related to what we've seen today is molecular dynamics. So often the accuracy of the molecular dynamics simulations are related to how good your force field models are, or to what degree of accuracy you want to achieve. And a lot of times, a lot of newer methods have involved using machine learning to learn those force fields to essentially be a better emulator for the molecular dynamic system. And maybe a couple other examples of things you might want to use this for are once you have one of these fast surrogate models, you can do uncertainty quantification, you can do active learning, maybe you can use it to solve inverse problems or do simulation-based inference. So there's a lot of useful reasons for having a fast surrogate model for your system. All right, so just quickly, so here on this first tab is just to set up install some packages. I guess I have to, yeah, there we go. Hold on a second. All right, yeah, okay. So yeah, the first couple of steps are just to get this package installed and set up. So these are just fairly standard packages. Like I'll talk a little bit about more of them later, but right now I'm just getting NumPy and the plotting packages. And so the data sets we're going to be looking at here are very simple dynamical systems data sets that you'll see commonly used for illustration purposes. So this first one is this van der Pol oscillator, which is this two-dimensional dynamical system that has a limit cycle. And so this code here is really just to generate the data set for us. So since this is a very simple data set, we can actually generate it right here in our notebook. Here is where we're defining the differential equation, and then we're gonna set up the integrator, give it an initial condition, set up the parameter mu, which is this parameter here in the system, and then just use the SciPy's ODE function to integrate the function. And when you do this, I can run this for you. You can see that you get this data, and here what you're seeing is it just this is the initial condition here, and it just eventually ends up in this nice limit cycle where it spends most of its time. So to set this up, the idea is let's try to train an emulator for this dynamical system. And just to show you the output of this integration function is you get a matrix or an array where it's 10,000 time steps, and this is a two-dimensional dynamical system, so that's the 2 here. And here I'm just splitting it into a training set and a test set, both with 5,000 time points. We're going to skip this for now. This is a different example that I have. And so the first method that I want to tell you about that was mentioned this morning is the sparse regression methods that essentially the goal is to explicitly get the equation of the dynamical system from the data. And in this case, the equation here is this two-dimensional ODE with a handful of terms here. And the idea with sparse regression is really you have some library, these thetas, you have some library of functions, and you're really looking just for some linear combination of these functions that give you this expression for the dynamical system. And choosing this library is part of this regression method. So in this case, I'm just going to have us choose a library that consists of polynomial features. And the goal in the end is, so I can basically take my data set, I can transform it by this library. So you can think of maybe these different thetas as different polynomial combinations of the different, in this case, we have a two-dimensional system. And so, for example, it'll include x and y and x squared and y squared and x times y. So these kind of polynomial combinations, maybe up to some degree, and then take that and then simply do a regression problem. And so this is actually a very simple on the face of it. And the useful, one tricky aspect of this is that you can imagine you can choose a lot of library functions if you don't know, you don't have a good sense of what the expression might be. Maybe you want to just choose a very large library and see if you can discover the expression. And of course, that can be rather tricky because then you run into these issues of with a very large library, then there might be, for example, more than one way of expressing this system, or maybe it becomes a little bit an ill-conditioned problem. And so what happens here is in the Cindy framework, what they do is that they also impose a sparsity. So the assumption is also that it's not just some arbitrary combination of the library, but it's actually a sparse combination of these library terms. And the method we'll be using here is a sparse regression method. Actually, let me switch to the other one. All right, so okay, good. All right, so here what I have set up for you is some code for performing. So yeah, so just to give you a sense of this approach, the way that sparsity is usually included in the Cindy approach is you perform the linear regression, and then you do what is called sequential thresholding. And essentially what it means is you choose some threshold for the coefficient. So if the coefficient is smaller than this threshold, you can set that coefficient to 0. And then you again apply linear regression and do thresholding again. And you repeat that process until it converges. So essentially the idea is that if there are small coefficients when you perform the linear regression, those will be thresholded first, and then you perform another linear regression with a subset of those library terms, and you keep repeating that until you get a sparse representation of the dynamics. And so, yeah, so what I have, so I think we're a little short on time, so maybe I won't go through. So here I initially had it set up to have you guys fill in some of these blanks here, so maybe you can have fun with that later. And what I'll do is, let me just walk you through the method real quick. Let's see. Right, so again, we're using this Van der Pol oscillator. And so there are actually nice libraries for doing this, but here I just have it written out just to give it be a little bit more explicit about what's happening, since it's a fairly simple algorithm. So initially, what you do is you produce your polynomial features. So in this case, scikit-learn has this really nice polynomial features function, so you can actually apply that directly and get your polynomial features. And actually, if you run this, what you'll see is that you can actually print out the names of these features. So you can see I have two different variables. So I have x0 and x1, and it gives me, so I asked for up to third degree polynomials, and so it gives me all the polynomial combinations here up to third degree. And then, so here I take this, I transform my initial data set. So now I have this theta, which is these transformed features, which are these polynomials. And then what I can do then is, in order to perform this linear regression, I also need to compute these time derivatives. And as you might imagine, time derivatives are, because you have to compute time derivatives, it makes this method fairly sensitive to noise. So there are situations where I think there are a lot of variations on this to try to address this kind of issue. But one issue you might imagine is if you have a hard time computing these time derivatives, then it becomes a much harder task to try to do this type of regression. Of course, the sparsity aspect is supposed to help regularize this. So what's happening here is here I'm going to do just a simple finite difference of my training data to compute this time derivative. And so now I have my features, I have my time derivative, and then we can perform the sequential thresholding. So this is set up so that so this becomes at a first glance, doing the linear regression is a very simple step, and in fact that happens here in the algorithm. The tricky aspect here is that you also need to mask out any components that are that you're thresholding out at each step. So what's happening here is I have a mask for the components that I'm keeping, And then for each dimension in my system, so I have a two-dimensional system, I perform the linear regression separately using this particular mask that I'm interested in. So here's my features, here are my time derivatives. We perform a linear regression, we get the coefficients, and then here we're just saving it in this coefficient matrix. And the final steps here are just every step of this loop, we're going to make sure the mask, we perform the thresholding, so we change the mask, so so anything below the threshold gets masked out, and then we also update the coefficients, so anything below the threshold gets set to 0. So if you run this, you'll see that in this case, it only took like 2 iterations, and this is like the final set of coefficients that you get. And if you remember, this is I have these 10 polynomial features, and this is 2 dimensions, and these are now the coefficients in front of those features. And if I just want to make it a little prettier, I can print out the actual equation that's associated with, and you can see that this matches exactly this Van der Pol oscillator that I was looking at. So before I go further, any questions about this method? Yeah.
Yes, this recursion. How is this recursion related to lasso regression?
Right. So another option for sparsity, right, is instead of doing this sequential thresholding, you can add a regularizer, right, and do like an L1 or L2. L1 for sparsity, right? And usually that's also a good option. I think what happens here is that if you apply this lasso regression, right? Then what happens is you tend to bias these terms, and you'll probably get a similar. You'll probably also be able to get a sparse result, but it also tends to give you not as good of a result as if you just performed this pure linear regression with assuming that you masked out the correct components, right? And there are like, maybe you could combine these 2 methods if you want to help introduce sparsity, but the simple version of the Cindy algorithm performs the sequential thresholding, and that seems to work fairly well. And if you want to really impose additional sparsity, maybe you could include this L1 regularization and then maybe slowly remove it in order to get more accurate values for these coefficients. All right, so so you can do this, and then here I'm just taking this model that I've created for the Cindy, so the model here is really just these features theta. I guess maybe I can make this bigger, it'll be easier. These features theta times the coefficients, and that's just the simple model for the system. And if I take that and integrate it, and obviously because it's found the right equation, I can predict the system extremely well in this case. So this is so if you can discover the exact symbolic form of the equation, that seems like the way to go. If you're expecting that the system that you're dealing with really has some symbolic expression, then either this or maybe even like a symbolic regression type approach people have been interested in the past few years might be the ideal case, especially if you can put some additional physics inductive bias, or the system, maybe based on symmetry, as it has to be some combination of a certain number of terms, then this is a very nice way of dealing with the problem, and gives you, as interpretable of a model as you can expect. So the next step here, let me see how much time are we? Okay, so the next emulators that I'll talk about are neural network emulators, or more like these black box emulators, where you have, in this case, you're assuming that maybe you don't know that this is you can write it down in this nice symbolic expression, and you just want some emulator that can do a good job, and you're maybe a little less concerned about the interpretability aspect. And in this case, what we can do is, for example, here, let's say we treat this as a discrete system. So we have these discrete time steps. So starting with x of t, we want to predict x of t plus delta t, and we can learn a neural network that directly maps from x of t to x of delta t. So this is fairly common and also reasonably easy concept of how you might train an emulator. And so here the code is also should be fairly straightforward. So if you're familiar with PyTorch, all we're going to do here is treat this as a supervised learning problem and train the neural network to predict this next time step from the previous time steps. So the setup here, so here I'm actually using this nice library called PyTorch Lightning, which saves you a lot of effort if you're tired of writing a lot of training loops yourself. So here, all I'm doing here is defining a simple 2-layer neural network or 3-layer neural network. And the idea is to map, in this case, my system is 2-dimensional, so map the 2-dimensional x of t to the 2-dimensional x of t plus 1. Here in the forward, I actually do a little bit slightly fancier. I'm actually recurrently applying it. So let's say if you wanted to recurrently apply this, you could predict future time steps by just recurrently applying f of this f. And so that's all this is happening here. You have this loop, and you're applying f of this neural network f to the previous time step. And here I'm just collecting here. And in PyTorch Lightning, a nice feature of this is instead of for you to write a training loop, you can instead just write the training step as part of the model and write the optimizer as part of the model, and then let this library kind of take care of the training loop for you. And here, so in the training step, what I'm doing is I'm taking a batch, taking that, feeding it through the model, and in this case, I'll produce a model prediction. And then from that model prediction, I can then do just a simple mean squared error loss to do my supervised learning and train this. And then, right, so here we're just setting up the data set. So we have to, it's a little bit tricky because you have to take my initial time series data set and split it into 2 parts. And you might imagine if you wanted to do not train just one time step ahead, you could train multiple time steps ahead. So this is just setting up that training data set. And then here I'm just defining the model. And the nice thing about this is for PyTorch Lightning, you can simply, once you define the model, you don't have to think too much about it. You can just take your data loader, plug it into this trainer, and tell it how many epochs you want. And you can just let it run, and it will, let me run this. And it will perform this simple supervised learning training for you. So I'll let that run for a second. So one thing we want to think about is after you run this, how are we going to evaluate this model? And so one simple thing is if you're performing supervised learning, you might imagine I could just take the test set, look at the mean squared error on the test set. That seems like a reasonable thing to do. And so here what we're doing is exactly that. So in this evaluation step, we're just going to take our trained model, we're going to apply it to the test set here, and then we're just going to look at this prediction that comes out of here and ask what's the mean squared error, this test error on this prediction for this one-step predictions, which just means like predicting x of t plus 1 from x of t. And in this case, if you take this and you run the mean squared error, you actually get, really nice, it predicts extremely well. The mean squared error is very low. But one thing to think about here is that because we're training this recurrent emulator in this way, this can sometimes be rather misleading because what you're maybe more interested in is how far in the future can you actually perform this prediction. And so instead of maybe doing this one-step MSE, which is very akin to what you would do in supervised learning, something you might want to do is recurrently apply this model maybe a couple times and see how well it's doing for a much longer term prediction, even though you're training, maybe you trained it on a very short-term prediction task. So here I can run this evaluation here, and you can see it actually does reasonably well. And you can see like there's a little bit, maybe it drifts a little bit, but overall, this prediction task this particular way of evaluating is probably much more meaningful. One interesting caveat here is this might seem like it's this you can kind of put anything in you want here and it will do a reasonable job. But one interesting feature that sometimes shows up, especially for these types of data sets, is, let's say I'm just going to change the seed here and retrain it. And in some cases, you'll see that the long-term prediction can vary quite a lot from the short-term case. So I'm going to let this run real quick. So again, like the one-step MSE is always very good. But what you'll often see is that the two-step MSE can sometimes vary quite a bit depending on how you train it. And I guess I don't have an explicit example here, but you'll often see that let me try actually a slightly different combination here. So what you'll often see is that the long-term prediction, this kind of short-term training, is not always indicative that you're going to do well in the long term. And this is maybe a little bit more evident on if you switch the data set to using that other data set that I provide, this chaotic Lorentz system. But in this case, we're looking at this, and even in this case where I'm just looking at this simple model with the single limit cycle, you might imagine one issue that you can come across is your data set is really only on this limit cycle. And so if any time, so here's a nice example. So this is another, I just changed the seed here, and you can see it's kind of gone a little crazy. So in the short term, it's actually doing reasonably well. But at some point, something really wild happens. And I guess part of the reason for this is that if you look at the training data set, it's really only on this particular limit cycle. So if I actually plot, here I'm going to plot the phase space diagram of this. So what you see is that this black line is this training data, or the limit cycle that you're supposed to be on. The black arrows are the ground truth, this van der Pol oscillator field. And this blue line, these blue arrows are actually what's being learned by the emulator. And you actually only expect it to be doing well near this near the training data here. And so once you go off from the training data, something very different could be happening. And what you're seeing here is that it kind of slowly drifts away from this limit cycle as it's predicting. And if it's in this case, if it has no data over here, you could very easily end up in a situation where it kind of spirals out of control, and this is something that you have to be careful about, especially if you have like maybe a single initial condition, or you're looking at a system that has like one of these limit cycles that tracks everything, and then you're dealing with the system where you don't really have much data in these other regimes, and so you might have to worry about the stability of this type of training.
You impose a boundary condition to enforce the beginning of the.
Right. So yeah, I think one option would be one option is you could just augment the data set, right? But another option is you could actually, something that maybe works a little bit unreasonably well is if you just add some noise to the data. What happens is then it learns to kind of self-correct a little bit. And so that in some sense that helps a little bit. I think boundary conditions in general, right? So it's kind of hard to control how the neural network is training, but you might imagine you could add another loss term and say like force the neural network to have a particular type of behavior. There are also methods where you kind of compute stability properties of this neural network, and you try to ensure that you're at least learning something that's stable, that doesn't diverge to infinity. Yeah.
Yeah, so would this mean that then the first method is more appropriate for this data? Is this what you're getting at, or?
Right. So I guess the first method is very ideal in a lot of cases, right? But it really depends on these very strong assumptions that it's a symbolic expression that you're fitting, right? And then you pick the right terms that is included in this. Also, your data doesn't have that much noise, so you're able to find this symbolic expression. And there's a lot of work actually currently on like these symbolic approaches to fitting or to discovering like these equations or discovering other properties. But I think that's still a bit of work in progress, because you might imagine that you could have a dynamical system where you don't expect it to be symbolically expressible at all. And then then you don't have, but obviously I think one aspect of that is like, if you do expect, you have a lot of physics knowledge, you do expect it to be some in the symbolic expression, then that's a really strong inductive bias to say that this is the only types of terms that I expect. And therefore it has to, then it's much easier, right, to get like a much more general behavior. So in this case, if I know it's this few terms that have to be in it, then there's only so many possibilities there. And in that case, I can fit almost the exact thing, and I can generalize arbitrarily well, right? And yeah.
No, yeah, that sounds good. Yeah, I was also wondering, I know we're a bit short on time, but at least for me that I'm not super familiar with running, it would be super useful to have time to do one of these exercises live now. I don't know if all of them, but maybe we could do one or two. Then how you were planning to do, I don't know. If we're supposed to finish at 5 sharp or if since we started late.
So I think the original plan is, I don't know if you wanted to start your tutorial as well, or did we want to, because I guess it might be a good place to stop for this one if you want to start yours. Yeah. So yeah, I mean, I think yeah, maybe if we have time on Thursday, then we can come back to this. But since we have, I think, a few other tutorials to get through, then it might be good to go through those first. But yeah, so what I have in the code here is I both have like the kind of blank version, tutorial version, and also the answered version with the code filled in. And yeah, I'm definitely happy to answer questions and work through it. And this is obviously the first draft I have of this, so I'm sure there are going to be issues with the setup. And just maybe very briefly, I'll say here that there are other types of emulators, more complicated architectures. Here I also included an example of a neural ODE, which is so you might imagine if you're trying to learn a continuous process, maybe instead of trying to do this discrete simulation, I really should be learning some continuous result. And so in this case, it's a very similar setup here. I have this very similar architecture, except instead of doing a discrete time step, I actually do an ODE integration here. There's a really nice code available for this. It'll automatically allow you to compute gradients through this. And once you do that, you can set it up and perform very similar types of training. And you actually see in this case, I'm using the same neural network, right? But because I'm integrating it using this ODE, I actually get much better long-term prediction performance. Because I'm using this kind of continuous ODE formulation. And in some sense, maybe that's saying that the expression for the ODE is much simpler than the expression for propagating at some finite time step. And so this is maybe something to think about when you're designing these types of emulators. So I think I'll stop here and I'll let Yihang give like a brief intro to his tutorial that he'll continue on Thursday.
Can you hear me? Okay, so since we are running out of time, so I would suggest everyone to open this answer keynote with me. And let's see. So if you really want to run the code, I would suggest you to start running this field block, which we try to install the packages and download the data set, because that really takes a while. But otherwise, I can start my tutorial today. So, hi everyone, my name is Yihang. I'm very glad to be here to share this tutorial with everyone. And today we're going to talk about how to use machine learning to predict the interaction between protein and ligand. And I think, so we have like 15 minutes left. So I will first give you a brief introduction about the science. So why we care about interaction between protein and ligand. And then from the AI side, I think we will mostly focus on about how to prepare the data set, because when the audience are from very different backgrounds, when talk about proteins, you might think protein in very different ways. I think some people might think about just fried eggs, and some others think about proteins consist of amino acids and they have very complicated structures. But I think they are both correct, but these are just different representation of the protein. But they are or not the representation that is favored by the neural network, because a neural network doesn't understand what is amino acids. You can only take number as input, so you really need to think about how to prepare the data set from how to clean up the data set and make it understandable by a neural network. And at the same time, because we are looking at some experimental data, usually they are collected from different labs. So the data set itself can be very messy. So you need to really figure out a way to go through them and clean them up. So that's one of the important things of the AI part. And then we will try to build a very simple neural network as for today, because as the data set actually we are looking at is not very big, so a simple neural network will do a very good job. But if you are interested, I would suggest you to go through the rest part of the tutorial when you have time. There we will show that when we try to make the neural network more complicated, how the performance will improve. And this is also, I think, a very important part for AI in science, because we have very different structures, and the different neural network architectures are developed to make sure that we can handle this data nicely. For example, like what Professor Graham Roxhoff mentioned today, like you have to develop some graph neural network to talk about to handle like real protein structures. And here that's the part about the network architecture. And then finally we will just show that, because when you train the network, we want to make sure that it really work well, so we will check its performance. That's something we usually do. So any question for the schedule? If not, then we can first talk about what's the ligand and what's protein. So here we are illustrating the protein as the blue block here. Usually they have different geometric structures, and the little cavity here indicates that there's some binding site for the ligand. And the ligand are usually just a small molecule which can bind to this binding set and binding site. And depends on the chemical property of the protein and the ligand and their geometric shape. The binding affinity between different ligands and proteins can vary a lot. So, and this is a 3D structure of the protein if you are interested in. And usually one way to describe, maybe even bigger. So usually we can describe this binding process using this equation of reaction. So you have a protein and it interacts with a ligand, and they form something called a ligand protein complex. And you can describe as I mentioned, some proteins may the binding affinity between protein and ligands can vary. So you can quantify this using something called the dissociation constant. And basically for the high dissociation constant, the proteins may not like, the ligand may not like to bind to the protein. And for the case with low dissociation constant, they have strong tendency to bind together. So why we should care about this? So because let me give you a very practical example. So one important application of this is trying to develop drugs to cure some disease. And usually a good drug has a good drug should has a good tendency to bind to its target protein. And since there is such a huge chemical space, it's usually impractical for you to just do experiment to search all search through all the ligands that you have. So that's possible. So if you have such a neural network model, it becomes easier for you to screen out those to come up with a better candidate for the drug. And to give you a number about this, is like usually takes more than $1 million and 10 years to develop a new drug. If you can use this to save a small fraction of the time and money, it would be a big deal. So that's what we are trying to do today. We are going to look at some data set we have, and then we are going to see if we can how we can use this to predict the binding affinity between protein and ligand. So any question? Okay, so we can, I hope you have already have some time to install these things. And so let me scroll down. So first, the data set we're looking at is called the PDB bind. It's a data set which I think that some PDBs track some structure of the protein and the ligand, and then there's an experimental measure quantity which indicate the which can give you some sense about interaction between them. And there are a few quantities. The one I mentioned is the dissociation constant, and there's some other quantity like the inhibition constant or the half maximum inhibitory concentration. These are also important quantities, but in some sense they are more relevant for the drug development, but I think the philosophy is the same, so we'll just focus on the first one. And we can really, so once the data has been downloaded, you can, so we need to, as I mentioned, we need to do some pre-processing of the data. So what is happening in this block is that we are trying to look at our data set and take out those columns that we're interested in. So here you can see if the prepared data set, we have the PDB code, and there's some, this is the, so let me try to give you a sense of what's happening here. So maybe if you are not from the biophysics side, you might be curious about what's PDB. So PDB is the short for the protein data bank, and you can search for the. You can search the protein here, as you can copy the code and then go to the bank and just search this code. You will find this will be the proteins that's actually in the data set, and you can just, if you want to just see the protein, you can just hide other things. And so this is the protein in reality in a nice representation, and this is the ligand binding rates. So together they are forming a protein ligand complex. And here we are taking out the experiment. So you can see that for different proteins, and the experimental measure quantities are very different. They can be the KD and the KI or the IC50. So and this are all about how to pre-process the data. So here, what is happening is that we need to append we need to add the molecular information to this data frame, and there's nothing too special here. And if we scrolling down, we will. So what's happening here is something I think a little bit important, because so as I just show you in here, you can represent the protein with a nice figure, but that's not something which can be easily understood by a neural network. And other way to represent the protein is to use the protein sequence, as I show here. They're just so here is just the sequence of the proteins, and for the ligands, there's another representation called the SMILE representation. So basically, once you get the sequence of the proteins, you will know what are the amino acids that made out of these proteins and their orders. And for the ligands, once you know the SMILE string, you can know exactly its chemical structure. So that's one thing we are going to try today. So what we are going to do is that we want to through this either the protein sequence and the ligand SMILE strings to the neural network and ask it to predict this association constant for us. So hope that the question is clear. And so here we need to, I think that here comes the first problem set in the other two notebooks. So basically, because the dissociation constants are recorded with very different units, because itself is a quantity that change in many different orders, depends on the property of the system. So first things you need to do is to look at the units and then convert them into just numbers. So that's something you can just try to play around. And so this is, you need to, so once this is done, so you will see the KD become just some numbers that you can, there's some numbers that you want to predict. And the other problem is that, as I mentioned, these numbers always lies in a very wide range. And for the purpose of training, usually we would like to normalize our data set. So what's happening here is that you first normalize the value between 0 and 1, and then you just take the you need, I think you first you need to so let's see what's happening. So if you you first convert the number into 0 and 1, and then you take the log of them to, I think you first take the log of the number, let me check. So yeah, I think so I will double check this part, but I think we can just assume that the data set is always normalized. And once you do this, you can try to test the code. So what's happening before this is that we actually split the data into the training and the test set. And if you plot their distribution, this will be the true answer. So what's happening here is that we just load the image with the true answer, and you can try to run your old code and see if you can reproduce exactly the same result. And so, okay, I see. So here, what's happening is that they first normalize the KD and then take the log, and other things you can is including this code that it will allow you to visualize the protein. So for example, you can see, you can randomly pick one sample here, and then you will, you will show the, you will show the structure of the, because here you will show the structure of the ligand. So we can see here, this is the ligand SMILE string, and it's always associated with the structure. And there's some problem in the notebook, so we cannot actually show the protein structure nicely. So let's just ignore that. It's okay, because we just want, so okay, now then it really comes to, there are a few question blocks you can try to answer. It's just mostly designed to help you to get familiar with protein and understand the problem setting here. And now finally, we finally comes to the part about training the neural network. So the network is actually very simple. We just need, what we want is that we want to include the SMILE string of the ligand, and then we have a neural network, and it will output the KD, which is the value we want to, which is the value we try to predict. And so, I hope everyone here is familiar with the data loader. Do I need to explain more detail about this? Okay, not then, okay. So basically what's happening here is that the only thing special here, it has a SMILE token which can convert the SMILE into just the one hot representation, which can be taken into the neural network. So this is the part that's a big special. And with that, you can prepare the data loader, and then you just need to do the training. And so here we have, then of course you need to build a neural network before you do the training. And here it's a very simple multilinear perceptron, and there's nothing, and it just has some this is very standard for any neural network. And then we need to define so once everything is done, I think we should be ready to train the network. So you can see once the network is built, you can you can see the structure here. So it's just two layers of nonlinear operation. And here, most of the functions are defined for you. You can use that to calculate the performance. And we can also calculate that on the test set to see how well the neural network perform. And for the training part, so here we allow you to choose something like the number of epochs you want to train the network, and you click the load way here, where we have train the model which you can load directly, which might help you to save a little bit time. For training this model, it takes a bit while. So if you just want to see the result, you can just load the just load the train model and just train it for the few steps and see how it works. And after that, we can see our training the training curve. So as we expected, the loss is decreasing, and there's a typo here. So the Pearson correlation should be increased, and the Spearman rule is basically the Pearson correlation basically quantify the linear correlation between your prediction and the ground truth and the truth, and the Spearman rule basically is just quantify the monotonic correlation, which already basically this might already be good enough, because usually for the purpose of drug development, we just want to figure out which ligand has a stronger binding affinity compared with the others. So that's the very simple part. So because we are running out of time, I cannot show all the details to you very carefully, but that's just the first part of the model. We try to predict the binding affinity based on the small string of the ligand. And you can think about other cases where we want to include the protein sequence instead to predict the binding affinity. And we can even make it a bit more complicated. So the rest part of this notebook contains all this information, including try to use protein sequence to predict the binding affinity, and use both the protein sequence and the small string to predict the binding affinity. If you think these are still very simple, we have a final case where we really look at the protein structure, and we convert the 3D structure into point clouds and use a relatively more complicated neural network to do the job. You can see that with different cases, the performance, how you can check how the performance changes and see if that see that if that agree with your expectation. So any questions?
Is the last transformer architecture like an SE3 transformer?
No, it's not. The last one is not. I don't think it's a transformer.
Oh, well, I was just guessing.
Okay, it's not. It's just point cloud neural net. So it's more the design trying to deal with the permutation environments. Okay, if not, then I think I would suggest everyone, if you have time, just try to go to the tutorial and we can answer. If you have any questions, just you can select us and we can answer that. And